want to tell you today about the role of the oceans in climate, and much of what we feel as far as climate goes has to do with the atmosphere, the temperature of the atmosphere. But it's important to realize that a very large part of the climate signal resides in the oceans. So just to give you an example of what I mean, if you think about the amount of heat that's contained in the oceans and atmosphere, the oceans hold about 1,000 times more heat than the atmosphere. And that's simply because the mass of the oceans is so much greater than the atmosphere, and the heat capacity of the oceans is much larger. Similarly, the oceans also hold much more carbon or dissolved carbon dioxide than the atmosphere. So the oceans hold about 50 times as much dissolved carbon compared to the atmosphere. So the carbon dioxide in the atmosphere is very much controlled or regulated by the dissolved carbon in the oceans. And similarly, if you think about water, the oceans contain 96% of all the water on the planet. Just about 2% is in fresh, 1 or 2% is fresh water, 2% is in fact ice caps. So the oceans play a really important role for regulating the climate and what we feel in terms of the atmosphere, but also the water, in regulating water, and the hydrological cycle, in regulating the CO2 in the atmosphere, in regulating the oxygen in the atmosphere, because about half the primary production or the fixation of carbon through photosynthesis occurs in the oceans. So we owe a lot to the oceans for our lives, but not many of us realize that because we live on land and we're terrestrial beings. But really, the Earth owes its climate largely to the oceans, and that's something that we really need to realize today. So what I wanted to tell you about today is really a research project that I'm very much involved in, along with a whole group of people. It's a very collaborative project, and science these days is done in groups of people. So all my colleagues, I owe them very much, and also my students who play a very keen or important role in this project. And also the funding agency. So I start out by acknowledging everyone, and the we refers to everyone in this project. And this project has to do with trying to better understand a region of the oceans which is relatively poorly understood. It's the Indian Ocean. The northern Indian Ocean is the focus of our study. And this part of the oceans is particularly important because it supports a very important climate system, the monsoons. So the monsoons are an enormous breeze, it's enormous land breeze in which, or ocean land breeze, in which the winds blow from the oceans onto the lands and some onto the land in summer, and then they reverse, the mean winds completely reverse. There's a huge seasonal change in the winds, and along with the winds, the circulation of the oceans reverse. But these winds carry a huge amount of moisture with them and bring rainfall to a large part of Asia, to South Asia. And it's interesting to note that about half the world's population lives in that part of Asia. About 1.5 billion people depend on the monsoons for their sustenance. And the monsoons bring water to, India and Malaysia and Burma and Pakistan and Sri Lanka and Indonesia, and there's also an Australian monsoon. So understanding this part of the climate system is very important because so much of the world's population relies on it. And as you might have guessed, the oceans play a huge role in the monsoons because all the water that comes into the atmosphere is really coming from the oceans. The oceans provide the heat and the moisture for driving this huge weather system or this huge climate system. So our motivation here is to better understand the role of the oceans in the monsoons. And the reason we started this project is because we realized that when you look at climate models today, or models that predict the weather or the weather over the time scale of a season, we found that climate models do a really poor job in this part of the world's oceans, in this part of the world. They do a poor job with the ocean and the atmosphere because the atmosphere is so coupled to the oceans through the monsoons. So this part of the world, really, the errors in the model are the largest. So why are these errors the largest? If you try to ask that, then we realize that as in this part, the atmosphere and ocean are very coupled. As I said, the atmosphere gets its moisture and heat from the oceans, and then the prediction of the oceans in the models is not working out quite well. The models create an ocean that's a little bit too cold at the surface, cold compared to observations, and then that doesn't drive the right monsoon system. So we started this project in collaboration with several countries. It's a very international project, and before you go into some region of the world's oceans, it's really good to reach out to the countries in that region. And we reached out in particular to India, also to Sri Lanka, and started this collaborative project with them, which entails several countries around that region. This project was funded by the Office of Naval Research, and it really brings cutting-edge technology to try to understand this problem. When we spoke to scientists in India, they told us that prediction of the monsoons is a very major problem for them, and one of the big concerns is the onset of the monsoon, but also the variability during the monsoon season or the summer monsoon season. So the rainfall comes between June and August to September, but it's highly variable. So you might have a period of very high rainfall for about 10 days, then you have a dry spell, and then you have another intense period. These are called active and break cycles, and they see a strong correlation between surface temperature of the oceans and these active and break cycles. So we really want to try and understand better what's happening here, how the oceans feed into the atmosphere. Now, the way we go about this is that we had a plan. We take all the data that's available. As I said, this part of the ocean is undersampled, but through the World Ocean Observing programs that are in existence today, there is data available. There are floats which are in the ocean that are autonomously making measurements, and we're going to go to the float lab to see some of these floats. And there is satellite data available from these oceans. And we find that this part of the oceans is very unique. It's very unique because it's one of the freshest oceans in the world. And so why is it so fresh? It's fresh because it gets an immense amount of rainfall. If you were to look at global rainfall from a satellite image, this part of the world's oceans just stands out. It's the region of the world that receives the highest amount of rainfall, as much as some places receive as much as 3 meters of rainfall per year, or all during the summer season. So there's a lot of fresh water that's coming into the oceans, and there's also an enormous amount of fresh water that comes from rivers in the surrounding region. So the rainfall that falls on the land, and you have the Himalayas, the mountains which are blocking off the winds. There's, the water is just flowing down the Himalayas and in enormous rivers. The Ganges, the Brahmaputra, and the Irrawaddy, they all flow into the Bay of Bengal. And this fresh water creates a surface layer which is relatively fresh compared to the rest of the ocean. So the oceans in general are very layered. There's light water at the surface and denser water below. The density varies by a small amount, but it creates this layering which makes it very difficult to mix the oceans. And in most places, ocean density is governed by temperature. So you have warm water at the top, the surface is heated by the sun, and this layering prevents the oceans from mixing very strongly. But when you do have winds or mechanisms that mix the ocean, you create a surface layer of the ocean which is called the mixed layer, which gets mixed by the winds and cooling. Now, in the Bay of Bengal, which is the region of the oceans that we are studying here, we find that the fresh water creates a light layer on the surface, and the density of that water is governed by the salinity or the freshness of the water rather than the temperature. And so why does this matter? It matters because the vertical structure, that vertical layering of the ocean, affects how heat gets distributed. So let me give you a thought experiment. Let me say that I have a region of the ocean in which this surface layer is well mixed to 100 meters. And then I have another region of the ocean in which I have a fresh layer which is 10 meters or 20 meters at the surface. And now I start heating both these oceans with the sun. In one case, you'll find that the heat mixes deeper because the mixed layer is deeper and the winds are churning up that heat and distributing it over the upper 100 meters. In another region where you have this freshwater layer, the mixing is not penetrating as deep, and so when you start heating the surface, the heat gets more trapped in that surface layer. And so you'll find that the surface temperature in these two regions of the ocean will actually differ even though the solar insolation is the same. And this is in fact something that we know happens in the Bay of Bengal. So during the summer, when the sun is out and it's really warm in that part of the world, the surface oceans heat up, but the Bay of Bengal, the temperature goes up very rapidly. That increase in temperature drives evaporation, and that latent heat then goes into the atmosphere and drives the circulation or affects the winds which form the monsoon. So our goal here was to try and understand how this freshwater layering affects that density structure in the upper ocean and how that affects the heat flux, and the heat flux from the atmosphere to the ocean, but also from the ocean to the atmosphere, both the heat and the moisture fluxes. So this is what I'll show you what a salinity and density section, temperature section looks like. So by section, I mean we are going along in a ship and we're making measurements in the vertical, and we have a whole transect that we are making with a ship. And that transect allows you to see what the temperature and density, salinity of that ocean is. Now, looking at that gives us some understanding of what the structure is, but we really want to try and understand what processes drive that structure. And an important role here is of people who think about theories and models and put those models together in trying to explain those structures. So I'll give you an example of a model, and my student Gualtiero is working with this model now. It's a model which describes the circulation or the flow field in the ocean as a function of heating, cooling, winds, and the initial temperature and salinity structure that you put into this model. And so we create in this model, just as I explained to you, a layer of light water as we see in the Bay of Bengal, and a layer of slightly denser water which is less higher salinity and less fresh, and then we start cooling this, in this case, this model from the surface. And this cooling of the model of surface essentially takes out heat from the ocean surface. So this is what you'd find in winter, and you see that that heat loss is distributed over a greater depth in the region where the surface ocean is mixed to greater depth. That heat loss is confined to lesser depth when you have a very fresh layer lying on top. And so you start with a uniform temperature on top, and now I apply the same cooling to both parts of the model, and what we find is that one part of the surface ocean gets cooler than the other part of the surface ocean. And I'll show you a clip from this model which will allow you to see, in fact, how the surface ocean is now responding, the heat flux is responding because of this difference layering in this density which comes from the fresh water at the surface. So models such as these, there are many kinds of models. We also have models of the entire circulation of the bay, and other people are working on these models. But models such as this allow us to understand the processes that are at play, the processes that create that density structure, and the density structure that affects the air-sea fluxes. So let me go on to tell you a little bit more about the measurements that we make in the bay. How do we understand what the values of these of the air-sea fluxes are? So one of the things I'm going to show you a little bit later today is these buoys that we put out in the ocean. So my colleagues here at Woods Hole, Robert Weller and Tom Farrar, are constructing or making ocean moorings, and these ocean moorings are put out in the middle of the ocean at various depths. They have a string of instruments, temperature and salinity measurements, which are made at different depths. And at the surface, these buoys have instruments which measure the atmosphere, and they can also measure the transfer of heat and moisture between the ocean and the atmosphere. So India has a number of these buoys in the Bay of Bengal, and their Ocean Technology Center, National Institute of Ocean Technology, puts these buoys out. Woods Hole has put out a very highly instrumented mooring just last November, We'll see how that mooring is constructed in a little while, and we'll be getting those measurements back later this year. The mooring is out for a year, and we'll put in another mooring, and we'll try to keep cycling these moorings so that we get continuous observations. Because getting observations over a period of time is very important in the oceans, because the oceans are not just static, they're evolving in space and time. So different parts of the oceans, we measure different things, but it's evolving all the time in time. So the same location, things keep changing, and this is why it's a difficult problem of having to measure both space and time. And if you really want to understand how things are changing over some period of time, particularly how global warming is affecting the oceans, we need sustained observations. And sustained observations over the period of several years actually costs a lot of money. I mean, having one of these, a single mooring like this can run into $1 million. So you can imagine how much it costs to maintain a mooring for a year. So besides the mooring, I'll show you some other instruments today, and those instruments are gliders and floats. We'll go to the float lab. Gliders are autonomous instruments. We are trying to automate a lot of our instruments. At the same time, we do have the need to go out on research vessels or ships. So we'll see a research vessel. We've made 3 cruises already in the Bay of Bengal, and this August we'll do yet another cruise on a research vessel called the Roger Revelle. And it's Scripps Institution's research vessel. We'll see one of Woods Hole's research vessels later today. And these research vessels are specially outfitted with all kinds of gear. They carry a lot of instruments. The back of the research vessel has a special crane, I should say, from which you can lower instruments into the water. And as the ship is going along in the water, the research crew works 24 hours a day in shifts because these cruises are very expensive. A day of a research cruise costs, just for the ship, costs something on the order of $40,000 or $50,000. So you want to really maximize the measurements you get back from one of these research cruises. You work throughout the day in shifts. You want to make sure the data is good. You want to make sure you get data. All kinds of things can happen with the instruments. In this particular study, our cruises are involving also scientists from India and Sri Lanka. And a large part of this effort is the collaboration, the international collaboration, because no one country can just monitor and measure the oceans. The oceans are vast, and we really need an international effort in studying the oceans. So it's our mission to try and involve these other countries, and also to bring these cutting-edge observations that we are pioneering through the funding of our national agencies to these other countries, promoting the use of some of the equipment and learning also from their empirical knowledge about their oceans. In this particular collaborative effort, we are respecting what's called the economic exclusive zones of the countries. So every country has an economic exclusive zone. It can get quite political, so working with the host countries in the region where you're working has a lot of advantages. And the work, of course, also benefits them, which is very important. So I'll tell you a little bit about life on this research vessel. This particular cruise that we are going on is very international. We have people from all countries, as I mentioned, India and Sri Lanka, and even scientists in general. Our scientists at Woods Hole are very international. The scientists get together in a lab in the ship. They plan out, before we go on the mission, we plan out in great detail what we are going to do, what instruments we are going to take, how we are going to make the measurements, what the cruise track is, what the cruise plan is, how many people are coming, which scientists are going to do what, who's going to be on what shift. There are several PIs, and we are all coming together to make these observations. At the end of the observations, we all go away, work on the data, but we gather very often to talk. And a lot is learned through these meetings and discussion. We sit around the table, we talk in small groups, we get together in larger meetings where people fly from across the country or meet in one place or meet through the internet. We show our data to each other, and different people are learning different things, and really the sum ends up being more than the individual parts. So the collaborative aspects are really, really important for this kind of study, because however much we try to sample the ocean, we are undersampling it. It's just evolving all the time, and we're getting measurements in some region. We're trying to extrapolate with theory and models to other parts of the ocean to understand how it works. Now, when we're in the ship, so once we go to this other country where we're going to make the measurements, there's some formality. All the equipment has to be shipped ahead of time. We've already sent a container ahead from Scripps, so all the different institutions right now, the study, there's 7 or 8 universities within the US, another 7 or 8 institutions in India. We pooled all our equipment together. We sent it to Scripps. A container has shipped from Scripps, and it will board the research vessel. The research vessels are all the time involved in research programs in different parts of the world. They don't come back home every time. Our research vessel is now in the Pacific, the Roger Revelle. It's going to meet us in India in a port called Chennai, in the port of Chennai, and the scientists will board the research vessel there. We'll be out for 4 weeks, starting mid-August, and have a plan of action. We're bringing several instruments, making something called underway CTD. That means while the ship is moving, we have something called a fast CTD, which measures conductivity, temperature, and depth through pressure. And so conductivity gives us salinity, temperature with a thermistor, a special probe for temperature, and then we also have acoustic measurements, what's called ADCP at the bottom of the ship, which measures the velocity or the speed of currents. And then we deploy a lot of autonomous instruments which we leave in the ocean. We deploy them in the ocean, and these instruments will be making measurements. Some of them will be left there for 6 months at a time, for a year at a time. We go back and collect them at the next cruise, or our Indian partners will go out and collect some of these instruments. And some of the instruments we deploy while we're on the cruise and then bring them back with us. There's a crane. There are several cranes on the ship. The instruments are lowered from the crane. There's something called a CTD rosette, which has bottles on it. These bottles are cocked open, and at different depths, the whole crane lowers this rosette into the ocean to a depth of 1,000 meters or 1,500 meters or whatever depth you wish, and it's brought back up by the crane, and the bottles pop shut automatically when you trigger them at the depth where you want to take water samples. So it's important also to measure the chemistry and the biology in the water. It's a very interdisciplinary problem. I've spoken mostly about the physics, but the chemistry and biology of this region is also unique. For example, the Bay of Bengal is an oxygen minimum zone where oxygen is very depleted, and we're trying to understand how that happens. And then there are various labs in the ship. So there's a computer lab where all these different streams of data are coming in. We see them on the monitor in real time, and people have to make decisions. So we have to make sure the data is good, that all the instruments are working at all times. But at the same time, we also have to make decisions as to where we're going to go. Shall we change our observational plan? Shall we follow a feature? Shall we go to a region which we are seeing lots of differences in density, or where the velocity is higher? Or sometimes we have to change our plans because of a storm. So the last time we were out there was a hurricane that came, and it significantly changed our plans as to what we should be doing next. So we have simultaneously making measurements of temperature, salinity, velocity. We measure the turbulence or the mixing, the rate at which things are mixing. People are analyzing the chemistry of the water. People are making biological measurements of oxygen, fluorescence. We'll be taking water samples to look at what kinds of phytoplankton communities live there. And we also measure the atmospheric variables, the wind, the incoming solar radiation, the heat fluxes, from which we can calculate the heat fluxes and momentum fluxes. And this is, at the back of the ship, we have instruments that go out and are making measurements. These instruments, some of the times, can be towed behind the ship. For example, we can drop a probe which measures temperature and salinity, pull it back and keep dropping it, so that as the ship is moving along, every 3 or 4 kilometers, we're getting a measurement in the vertical of temperature and salinity to look at that layering of salinity and temperature. And the shifts work 24/7 throughout the cruise. Once we get underway, we get our equipment going. We we work 24 hours a day in shifts to make sure that everything is going as planned. At the end of the day, people get together for a meal, and we sit around typically and talk about what we have seen that day, or talk about each other's science, so that we get inputs from everyone and try to, really further our scientific learning as a group. As I said, that's an important part of this research, and we also do it on the ship when we're at sea. What I'm working on in this study is trying to understand the dynamics of the upper ocean, the dynamics in response to input of solar energy, and in response to this fresh water that's coming out of the bay. This fresh water that comes out of the bay not only creates a layering in the vertical, but you have horizontal differences now in salinity, and also horizontal differences in density. And these horizontal differences in density lead to a very dynamic field of ocean currents and eddies. So the ocean is very dynamic at all scales. You have currents and eddies at large scales, but you have swirling motions and eddies that are occurring on scales of 1,000 kilometers, 100 kilometers, 10 kilometers, 1 kilometer, and down to the smallest scale of meters. And I am thinking of how these eddies or these swirling motions help to stir this fresh water around, mix it, and transport the fresh water that's coming all in the northern part of the bay out into the southern part of the bay, at the same time affecting this density structure so that it has an effect on the air-sea fluxes of heat and moisture. And that feeds back into affecting the monsoons. So our long-term goal through understanding these processes is, once we understand these processes better, we can incorporate them into models that cannot resolve these very small scales. By small, I mean kilometer scales that we are able to look at with these special models and these special tools of observing. The climate models have grids or spacings of about a third of a degree in latitude, longitude. That's about 30 kilometers. So they don't capture all these smaller scale processes. But we are able to understand them now much better, and are starting to understand them through these observations and modeling. And our next step would be to try and take this understanding, put it back in the climate models, and improve their ability to forecast, predict the ocean's temperature and the monsoon.
This area we call our high bay, and it's a place where we prepare instruments and boxes for cruises. Packing lists will be made, and everything will be loaded into shipping containers with forklifts to be shipped off to the cruise destination. So these are the buoys that we use, and there's a big square hole in the top of this buoy. It's a 2.8 meter buoy, so about 10 feet across. And inside that big square hole, we'll put one of these, we call them buoy wells. So it's these big steel boxes will be filled with batteries, essentially, and computers. And then on the buoy top, we'll have instruments. And over here you can see an instrumented buoy that we're testing. So we call this burn-in, and we run these instruments for about a month to test that they're working before they go into the field. And so our group measures surface meteorology from these buoys, and the goal of that is to understand the exchange of heat and moisture between the ocean and atmosphere, and the exchange of momentum from the wind pushing the ocean. And so we're measuring solar radiation, infrared radiation that comes down from the atmosphere, sea temperature and currents. We're measuring the winds, humidity, air temperature. And from these things, we can combine these measurements to estimate the exchange of heat and momentum and the evaporation from the sea surface. We're measuring the rainfall with rain gauges, and the buoy will stay out in place for about a year.
So Tom just showed you one of our surface moorings. This here is one of the pieces of instrumentation that we have clamped along the mooring line, and this measures subsurface currents. This is a vector measuring current meter, and you can see that it's got two axes here that measures currents flowing in two different directions. In addition, we also measure temperature and conductivity up and down the mooring line, and we use these. These are a Seabird 37. You can see we have a whole rack of them right here, and this is probably one of the most measured parameters in our mooring is the temperature and conductivity. With temperature and conductivity, we're able to determine the salinity of the water bodies, and that is one of the most important measurements that we make.
So these are autonomous underwater gliders, one variety of them anyways. So what they are platforms for us to attach a bunch of instruments to. And what they do as a platform is go up and down through the water, so they're able to change their buoyancy. They do that by moving water or air in and out of the pressure case, or in and out of the hull, and then changing their volume. That causes them to rise or fall in the water column. And as they do that, they're able to pitch their nose down as they're descending and up as they're ascending, and that lets them go through the water in a zigzag path like this. So every time they come to the surface, they're able to communicate. In these gliders, there are antennas for GPS and satellite communications in the tail. So they come up to the surface and they stick the tail up in the air, and then they can send back data. They can get new commands from us. They do that once every few hours, typically, depending on how deep they're diving. As far as the types of measurements they make, all of these gliders measure temperature and salinity profiles. They're also able to make estimates of currents. They measure optical properties such as chlorophyll fluorescence. Some of them, one down there further down, has a current profiler, so it can not only measure the averaged currents, but the actual profiles of currents. In terms of endurance, these vehicles are typically able to be deployed for weeks to months at a time, depending on the type of batteries we put in them. So in that time, they can cover hundreds to thousands of kilometers through the water. They don't go very quickly. They only go about half a knot, so about walking speed, or even less than walking speed. But because they can stay out so long, they can cover a long distance. So overall, the gliders are a great tool for giving us long duration, high resolution measurements out in the ocean so that we don't have to be there to collect them. They send back the data in real time, so we have the data coming back to us all the time. When we're able to put a fleet of these out, like we're planning to do in the Arabian Sea, we can collect lots of data from lots of places. We can fly them together in different kinds of patterns and collect pretty unique data sets.
So this is a Argo profiling float. It's an instrument that measures temperature and salinity in the water. Currently, there are over 3,000 of these in the world's ocean. It's part of the Argo program, which is an international program to seed the world's ocean with many of these to try to provide global coverage of measurements of the upper ocean temperature and salinity. The float itself consists of a sensor at the top, which is the part that actually measures the water properties. And then the rest of it is a hydraulic system that makes the float go up and down in the water column. These floats are capable of profiling the top 2 kilometers of the ocean, which is roughly about half of the ocean. They go out, we can program them with different missions. Most of ours profile once every 10 days, and that's chosen as a time period that meshes well with ocean variability and maximizes how long the floats last in the water. Our floats typically last from 4 to 5 years, and we've had some last 7 to 8 years. So they're very long-term missions when we put them out. The technology is very much like the glider technology, except it's simpler. We've taken the wings off, and instead of gliding around, we just go up and down. Horizontally, we drift wherever the currents take the float. But by making things simpler, we've reduced the cost, and that's why we can get so many in the water. The ocean has always been poorly sampled or undersampled, and by having an instrument that we can deploy in large numbers, we get many of them into the ocean. Most of the time, the float is down at 1,000 meters depth in the ocean, and there's not much going on there. These floats only spend about 15 minutes at the surface. They need that time to get a GPS fix so they know where they are. And then there's the antenna here, which transmits the data back to us via a satellite network. And that all takes place in about 10 to 15 minutes, depending on how much data there is. And then the float sinks back down. So we try to minimize the time at the surface, both for avoiding obstacles and also before avoiding fouling of the sensor. There's lots of biology at the surface. When we're deep, there's less concerns about biofouling of the sensors themselves. So one of the strengths of the Argo program is that it's an international program, and all the data that we collect is publicly available in near real time. Usually within 24 hours of the profile actually being recorded by an instrument, the data is placed at a public website, and anybody has access to that data and can use it either for their scientific research or for weather forecasting.
My name is Chad Smith. I'm the Assistant Marine Operations Coordinator here at Woods Hole Oceanographic. And what I do is essentially manage the research expeditions on one of our two ships, the research vessel Nor, where we are today. Our missions can range anywhere from the full gambit of oceanography, geology, physical oceanography, climate research. We have a very diverse needs of the scientific community that we have to meet. The aft deck of the Nor is where a lot of our action takes place. As you can see, the deck has a bolt pattern which allows us to mate up any equipment, winches of any variety, and bring it to any ship in the U.S. research fleet and bolt it right down to the deck. That facilitates our mobilizations of operations. Most anything that goes is deployed from the Nor's stern, goes out from this A-frame that can be towed or vertically dropped. We deploy a wide variety of equipment from the Nor. It can be as diverse as a vertical cast CTD rosette to an aerial drone that has to be launched and recovered on our decks. All of these things can happen in the course of a month. Because of Nor's versatility as a general oceanographic vessel, she's not specialized or set into any one type of mission. Therefore, she fulfilled a very crucial role, catching a lot of different operations that need to go from U.S. ships. Here we are on the bridge of the research vessel Nor. Being a research vessel, Nor's bridge equipment isn't appreciably different from other vessels in the U.S. merchant fleet. We have radars that are for navigation and collision avoidance, paper chart plotting, as well as computerized chart plotters. We also have what's called dynamic positioning. If you see here behind me, you'll note an absence of a large ship's wheel. We have several smaller controls on our helm, which control the control surfaces that make up our dynamic positioning system. What dynamic positioning is it essentially allows the ship to stay in one geographic position as we conduct research. It also allows the ship to be extremely maneuverable, which makes docking, which normally requires complex maneuvers, greatly simplifies the process. Other things that are controlled from this bridge, all communications that come in, the command of the vessel when underway and when conducting operations. And you'll also notice a few things that look a little bit out of place, such as this Navy-style intercom and a sound-powered phone. This is essentially a highly engineered version of two cups and a string, and it's the way we communicate on the vessel when power is down. Nor is actually built and owned by the U.S. Navy, and she's been operated by Woods Hole Oceanographic Institution since the late 60s.
I'm from a group in Cape Town, South Africa, and I'm working with Armada, primarily in the Southern Ocean. So I'm visiting here for a couple of months. I'm doing my PhD. And the group that I'm working with in Cape Town, we work primarily in the Southern Ocean, which is a far away from the Bay of Bengal, but still equally as important. And we use these glider platforms as well because the Southern Ocean is a very rough and dangerous place to be over long periods of time. So we put these guys out. These are surface gliders, so these guys remain at the surface of the ocean, and then the diving gliders have been explained. And how we do our sampling is that the surface gliders remain at the surface and the diving gliders dive just below them. And in that way, we're able to combine measurements of the atmosphere and the ocean to form understand the symbiotic relationship between the two.
I'm a graduate student working on my PhD. And this summer we're going to the Bay of Bengal in the Indian Ocean on a ship very similar to this, on the RV Revel. We'll be collecting various data for a whole month using CTD casts and gliders and floats. And with all these platforms, we try to measure the currents of the ocean, the salinity, the temperature, the atmospheric conditions. And we're hoping to use that data and combine it with modeling data to better understand the upper ocean structure and its interactions with the atmospheric monsoon system. And I hope to get an interesting PhD thesis out of this.